Welcome to the Control Engineering webcast, How to Tune Servo Systems for Optimal Performance, Part 2, Feed Forward and Nonlinearities, sponsored by Aerotech. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of the webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you're having technical problems with audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Type questions for our speaker in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of the webcast. We will now have a word from our sponsor of today's webcast, Aerotech. At the conclusion of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned after the video for today's presentation. I'm happy to introduce today's distinguished speaker. Dr. Profeta has more than 30 years of experience in technology-driven companies. He is the director of the Control Systems Group at Aerotech, with P&L responsibility for the controls, drives, and motors area. In this role, he works with companies to design and select control system architectures that result in increased machine performance while minimizing component cost. He has earned a Bachelor of Science, Master of Science, PhD, and an Executive MBA. He has been awarded 5 patents and published 43 papers. Dr. Profeta is also an adjunct professor in the Electrical and Computer Engineering Department at University of Pittsburgh, where he teaches software engineering. To start today's presentation, Joseph would like to begin with a video. Here it is.
Try to punch it.
All right, Joseph, please go ahead.
Okay, thank you, Mark. So I'm sure we've all had that experience in the video. However, if you watch part 1 of the webinar series, maybe you've had that less frequently. So we'll deal with the standard control problem again, and what you see here depicted in the block diagram is a controller with a plant and a feedback, and our goal is to have the output of this system Y of S track the input of the system YD of S. In part 1, we talked about using a Bode plot to look at the system characteristics, measure the gain and phase margin, which give us an idea of the stability of the system, and then putting in a low pass and notch filters. What we want to do today is focus on the feed-forward gains and dealing with some of the nonlinearities that are in the system. So specifically with the feed-forward, the typical scenario might be to do a step response and then change the gain of the feed-forward and see how that affects it. So you can see here a simple point-to-point move. It's a trapezoidal style move. And in the middle bar, you see the position error of that move, and the gain AFF is equal to 0. And a trial and error basis, I just put in AFF equals 100. I rerun the move, and I see, oh, okay, I did have some small reduction in the peak error, which is what I would have expected. But now the question is, well, how much bigger do I make AFF, or should I make it smaller, or what should it really be? So there are some methods that we can use to make a much closer guess the first time and find the optimal values for AFF. The first method is to, in the frequency domain, take and match the inverse feed forward to the plant, and I'll show you how to do that in a second. The second method is to look at the closed loop response and minimize the peaking by changing AFF. And then the third is to look at the feed forward current and maximize that value, and we'll take a look at how to do that. The basic questions, well, first, what even should the feed forward structure be? What is the best feed forward structure? And the second is, once I have those, what gains do I use in it? Where do I add the feed forward into the system? And when should I add the feed forward into the system? So we'll take a look at each of those questions and answers briefly. So I have a system here. You'll notice that this difference from the first block diagram I've shown, I'll just assume unity feedback, so H of S is equal to 1. And I have the same plant, GP of S, and I have the same control law, GC of S, which is usually a PID type controller. And we've added in the feed forward transfer function, GFF of S. And that takes its input from the command and then is inserted before the plant and after the control law. The responses that we want to use here to set this feed forward are to look at the plant response, look at the feed forward and the inverse feed forward responses. We'll also later on look at the closed loop response and the sensitivity analysis at the end. So just as a quick reminder, right, the feed forward comes from the command. We insert that into the system before the plant and after the control law, like shown here in the yellow highlighted diagram. And if we're using block diagram analysis, simply the output of the block, in this case YFF that we're interested in, is equal to the transfer function of the block, GFF of S, times its input, YD of S. And you see that on the right side. And we'll use that simple relationship in determining what the feed forward should be. A couple things to make note of. The feed forward really, if we knew the plant exactly, would be all we really need to control the plant. If we were precisely in the structure of the plant, all the parameters of the plant exactly, and there were no disturbances, we could just have a feed forward control and put in the input, and we would produce the appropriate output. So the feed forward really is the most authority in the loop. The highest current should come from the feed forward. And the feedback is really to accommodate these things we don't know about the plant, the parameters, the structure, maybe the resonance structure, and some of the disturbances that will occur. The basic reason we use feed-forward is we're trying to minimize the overshoot in the system, and when we minimize the overshoot, usually we can get a little bit better settle time, as well as a better contoured motion. Ideally, this feed-forward is the inverse of the plant. Our goal is that our output, Y, should be equal to YD, and so if I just write the transfer function from the output to the input, I have Y of S is equal to GP of S, the plant, times GFF of S, the feed-forward, times YD. So if I compare these first two equations, then obviously GP times GFF equals 1, gives me exactly what I want, and therefore the feed-forward should just be the inverse of the plant. So let's take a quick look at how that works with a frequency response. So here's my plant, and I'm going to focus on just the GP of S that's in red. And let's assume that I just have a standard servo motor, and I want to regulate its velocity, its of rotation. Then my plant, and it has some inertia, and let's lump the inertia and the power amplifier gain together. I would have a transfer function that looks like 1 over 2s from the input of the power amplifier to the output of the velocity. If I look at the frequency response of that, then my Bode plot looks like a slope of -1, which is falling at 20 dB per decade. And I set this one, you can see it has a crossover here of about 0.6 radians per second. The phase is what we would expect, -90 degrees. Now let's look at the feed-forward. So we're going to focus on GFF, the red block, and if GFF is just the inverse of the plant, then GFF should be 2s. And I look at the Bode plot of that. It looks like a slope of +1, 20 dB per decade, also crossing over at 0.6 radians per second. And the phase of that, as I would expect, is +90 degrees. Now, if you remember from last time, the great thing about Bode plots is as we multiply the transfer functions together, we basically add the Bode plot. So if you would look at the gain of the plant and the gain of the feed-forward, say at 0.6, it's both 0. So 0 plus 0 is 0. And if you look at and pick off a couple of points, you'll see that if I add these two gain plots together and look at the resulting path from the output to the input, GFF times GP, I should have just 1 over S times 2S equals 1. And the Bode plot, in fact, shows 0 dB, which is, remember, a gain of 1. And if I look at the phase, again, the phase adds, so -90 and +90 is 0 degrees. I would perfectly follow the input of the system with the output with this plant and this feed-forward. Seemingly simple answer. However, the problem is the inverse of the plant is not always physically realizable. For instance, let's say now we wanted to look at, again, a servo motor, and let's look at its position output. And so now my plant would be 1 over JS squared, J being the inertia. And if I would look at an inverse of that, that'd just be JS squared, but I can't really build one of these. It's not a physically realizable system. And so I have to add something to the feed-forward that's not really the exact inverse of the plant. So the way to do that is to maybe put a high-frequency poles that will not affect the region of interest in the frequency, or try to build something just close. The more complicated your plant, the more complicated the feed-forward compensation could be. You could have a very complicated inverse feed-forward. However, it's usually just good enough to try to fit the what's called the inertia line of the plant, the 1 over JS squared. And if you do that and ignore the resonance structures that might be in the system or the frictional component of the system that's going to affect the low frequency, what you find is this is, for the ease of implementation, the best bang for your dollar. Remember, we're not going to be able to deal using this feed-forward structure the unknowns of the plant or the disturbances in the plant, but it will help us quite a bit in minimizing or create a more optimal performance step response of the system. Okay, so here's a real multi-loop control system, and on the right we see the GP of S, the plant. I have the inertia shown, 1 over J. I have a resonance structure shown, which is this S squared plus 2 xi omega 1 S plus omega 1 squared over the denominator S squared plus 2 xi omega 2 S plus omega 2 squared. This is just a resonance anti-resonance pair, which occurs in most systems. You see some sort of resonance structure at the higher frequencies. And then 2 integrators to get us to the position. I measure the position, I bring that back, and then on the left I have the control law. I have the commanded value, YD. I subtract the feedback from that and produce an error, and then the error goes through a proportional gain. I then subtract out from that an estimate of the velocity to create a velocity loop, and I have a proportional integral gain in the velocity loop. And then I have filters. This is where we would usually put a low-pass filter or a bicloud filter or a notch filter to help minimize the effect of that resonance. What you see in the red is the feed forward. So the S squared times KFF is the acceleration feed forward. We're going to cancel out the inertia line of the plant. And then I can also create a velocity feed forward. So I have S times KVFF. And this will help minimize the overshoot due to the velocity. And then this is not the only place that we can stick the feed forward. Notice that both the acceleration and the velocity feed forward shown here are inserted right before the power amplifier. This is a very common place to do that. However, with a multi-loop structure, you could also have a feed forward path from the input YD of S to the input of the velocity loop. And that would also be a valid method of feed forwarding information into the system. I'm just going to focus for the rest of the time on feed forwards which go into essentially the current node. So the top 2 red boxes. The other question is, well, should the feed forward be added after the filters or before the filters? Commonly, I like to add them after the filters. However, if you would expect that your command is going to have frequencies which will stimulate the resonance in the system, it may be advisable to put them before the filters. And then what you'll do is you'll filter out those frequencies which would stimulate the resonance and possibly have a more stable system in terms of its responses to the command. So we're going to see a video of setting the feed forwards.
I have a standard servo motor set up with a small inertia on the shaft. Let's start out with a simple point-to-point move. We'll follow a standard trapezoidal motion. You can see the acceleration here, deceleration here, and during the accel and decel, we get some peak position errors. During the constant velocity here, you also see some following error. We'd like to minimize both of these. As you would expect, during the accel and decel, we push more current into the motor to move the inertia, and much less current here, really just pushing against the friction of the motor. So let's try to adjust the AFF, and the usual trial and error is, okay, let's just put a number in and see how much it changes the system. So we'll create a new plot. So rerun the move. And now if we look at the overshoot here in the position air, we're sitting at about 0.66 degrees. And if we would compare that to where we were 0.75 degrees. So we have minimized that overshoot some. And we could sit and keep adjusting AFF and watch the position air reduce until we get to some optimal point. But the other method that we've talked about is looking at the frequency response of the system and looking at the inverse feed forward. So let's just do a frequency response on the system. If you'd watched part 1, you would have seen this before. We're basically putting in a series of sinusoids at distinct frequencies. We're measuring the input and output of the system. We're in fact stimulating at the power amplifier and measuring the output. And then we can paint what is here the loop gain and use that loop gain to assess the stability. As we did before, we would look at the gain and the phase margins, have the gain margin be more than 6 dB and the phase margin more than 30. What you'll see is this is a very robust system and it's stabilized with sufficient gain and phase margin. There's not a complicated load on the motor, so not a lot of dynamics out here at the high frequency, but we do notice a flattening of the curve here at the lower frequencies, which indicates some friction in the system. So now let's go and look at the plant responses, which is what we're interested in, trying to match to the feed forward. And if we look at the plant and measure what is the slope of this curve, we see that the delta from 20 to 200 hertz, which is 1 decade, is shown here as about 40 dB. It's exactly what we would expect. We're looking at an inertia that we're spinning, and the slope should be a -2, falling at 40 dB per decade. And what we would expect for the phase is that we would be at -180, and you can see here basically at -180. So we have essentially a rigid body. Now let's go look at the feed forward response. And what we see here is a positive slope, about the same as this, as it is the inverse of that. But it's a little hard to match these up when we look at the feed forward. So the more convenient thing is to look at the inverse feed forward. And now what we see is the inverse feed forward is the same slope, but it's not the same gain as the plant. And so we want to match those up as closely as we can. Here's AFF. It's set to 100. Let's move it to 200. Now remember, we're looking at the inverse feed forward, and so in order to move it down, we actually have to raise the gain. So I'll go to 200. You can see the line for the inverse feed forward move down closer to the plant, and I can continue to do that and make some quick guesses. And it looks like 750 matches this inertia line fairly well. You can't get an exact match because of the dynamics and the friction here, but for the most part, we've matched the feed forward to be the inverse of the plant at this point, with a value of AFF equal to 750. So let's accept that, and then let's go back to our move and do another move. Need to enable the axis. And if I look at the overshoot here of the system, it's about 0.21 degrees, and if I would compare that to the previous one, it was 0.66. So indeed, I have minimized the error. Now, let's go back to our loop transmission. We did the best fit we could here. However, if we zoom in on this area that is really the inertia line without the friction and the dynamics here, we might get a little bit better fit. So let's just redo this response from, let's say, 10 Hertz to about 200. And by default, we always paint the open loop when measuring this response, but it will flip us back to our plant and inverse feed forward when it's finished. The other thing you might notice here is this constant velocity on. If you're having a system with a lot of friction, sometimes you turn that on to move the axis very slightly while you're doing the loop transmission so that you can get a response that is divorced of the friction. Okay, so now we have, again, our plant and our inverse feed forward. We had 750 in, which you can see gets very close. I can kind of see that the plant is always a little bit below that, so maybe I could refine my gain a bit more, and I'll make a guess of 825, and I can see that it kind of splits the line or the difference of the plant, and so I'll call that my final selection for the gain. I'll come back to the transient response on one more quick response. You're going to need to enable the axis. And when I look at this, I have now overshoot of 0.08 degrees max as compared to the previous 0.21. So I've been able to, by matching the inverse feed forward to the plant, calculate the feed forward gain necessary to eliminate as much overshoot as possible.
Okay, so now that we know how to set the feed forward, just in summary here, right, I show the plant and the inverse feed forward. We just set the AFF gain to match that line, and that generally will give us a very good value to use for AFF. The second way that I mentioned was to use the closed loop response to set the feed forward. So here I show the closed loop response of the same system, and I can see a peaking here of about 5.5 dB. So I would expect a little bit of oscillation in the system from that. I don't like to have peaking more than 3 dB usually. So what I'd like to do now then is change, also note that the bandwidth here is about 54 Hertz as measured at the usual -3 dB point. And now what I'll do is I'll change AFF to 750 and I'll plot the same closed loop frequency response, and what you can see is I got rid of all the peaking here. So that AFF will minimize that peaking in the closed loop response, and I can use that if I don't have a inverse feed forward to lay over the plant. I can usually use this as a substitute for that to get very close to the right feed forward as well. And you might note when I look at the closed loop response, including the feed forward response, that now my bandwidth at the usual -3 dB is 369 Hertz. So I've considerably increased the closed loop bandwidth of the system using the feed forward. This is why we get a much better step response in terms of move and settle when I use the feed forward. The third technique is really to just use the feed forward current and try to maximize that. As we said in the beginning, if we knew the plant exactly and had no disturbances, all we really need is feed forward control. So the feed forward control would produce all the current necessary to place into the system. That's the case whether you have a feedback loop or not. So even with the feedback loop, we should try to maximize this feed forward current. So just as a reminder, we're going to look at this current coming out of the block S squared KFF, which takes its input from the command and produces a current input into a command input to the amplifier. This is the current we're interested in maximizing. And then the current coming from the control law, which is the current out of the filters into the power amplifier, this we're going to try to get as close to 0 as possible. And the only reason we would have a current coming out of the control law then is to accommodate for whatever disturbance forces are in the system that we don't have modeled in the feed-forward control. So we'll see a video of how to minimize that current now.
So let's do our standard move again that we've been working with. I have AFF set to 0, BFF set to 0, and we see our overshoot here where it was before at 0.76 degrees. We see the current here, and what we're going to try to do is match our feed-forward current to match the total current. That would make the current coming from the control be 0. And so if I just do an auto step here where I basically repeat the same move, and I can dynamically change this value. So if I change AFF to be 100, what we see is the feed-forward current matches the shape of the current command, but not quite as much. It's 0.05 amps, whereas here we have 0.5 amps. And so we're producing more current through the controller than we are through the feed-forward path. And we did, again, eliminate some of the overshoot. We can change this and increase 300. And again, we see the amount of feed-forward current increase. We don't see any current during the constant velocity. Remember, we're differentiating twice the command, which would give us a 0 current output. And as we know from our previous exercise that around 825 is about the right number. So 500 again increases. Let's just jump right to 825. And if we look at that, we see, okay, a current of about 0.42 amps. And if we look here, we're about 0.7. So it's about equivalent. We could refine this a little bit, but you see that we have indeed matched the current of the feed forward to the current, the full current, and minimize the current coming out of the controller. And that, again, gives us the same answer of minimizing the position.
Okay. As with most things in life, you find timing is everything. So what we need to talk about now is what's the timing of that feed forward. So today, up to now, we've just really treated the system as a continuous time system, including the controller. But the fact of the matter is most controllers nowadays are digital controllers, and we need to deal with the fact that we take samples of the sensor and then produce an output at some sample period or frequency. Typically, these frequencies vary anywhere between a kilohertz to 20 kilohertz, depending upon the controller that you're using. And each of the loops in a multi-loop controller is not always at the same frequency. So the current loop is often much higher than, say, the servo loop. And so the question then again is, where do I inject that feed-forward current in time to help optimize the system? So I've shown here in the orangish box here, and you can see the two red feed-forward boxes represented in the digital or the Z domain. And then if I look at, say a position or servo loop that is operating at a kilohertz and a current loop that's operating at, say, 20 kilohertz, then I'd have quite a few samples to select when that feed forward gets injected into the current node of the system. Really what you need to do in this case is do a similar step response like I showed you in the last video, and advance or retard when that feed forward is inserted into the system, and see what the effect on the overshoot is. Essentially, what you're doing is trying to match the phase of the feed forward with the phase of the plant, so that the inverse feed forward cancels that out as close as possible. So the effect here will be minimal. This is kind of the last little, polishing that you would do on the feed forward tuning. So let's just kind of put all this together, and really, I've described a couple different techniques. When I'm tuning a system, I'll use all of these things to try to find and zero in on what really is the best set of gains for a system. So you can see on the right here a standard linear motor stage with a mass attached to it of 7 kilograms, and if I include the mass in the bracket and the carriage, I'm 21 kilograms for the total load. And let's just do some simple moves and look at what the total time is to do the move and settle, and what the peak overshoot looks like, and what the tracking error of the system looks like. So with no feed forward, AFF, VFF equal to 0, I do my base move, and I measure that, and I can see, you see a little star here in the middle strip chart, shows me that, I'm somewhere around 0.34 seconds or so for the move and settle, so that I can settle within the settle time I've set. And my max error is about 36 microns if I look at the peak error at the beginning of the move here. I'll set my AFF equal to 629, which I can just do with a simple hand calculation on a piece of paper. And apologize for the typo here. This KEND should be KENC encoder. And if I do that simple calculation here, I see that, well, I've minimized my position error. It's down to 13.5 microns. And I can see that I've also shortened the move and settle time of the system. Now, I also should have noted that here now I can see the feed forward current, and it's approaching the total, but it's not exactly the total. I ran the Autotune feature on this controller, and I got down a little bit more in terms of the position error, a little bit under 17 microns. And again, I can see the current matching up more closely to the total current. So this feels like a little bit better settings for the two gains. And then I ran a second tuning technique on it to see what I would get, and I got, oh, just a little bit better in that response. And then I did a little handcrafting and said, okay, if I was going to optimize just this move, could I dial it in just a little bit more, and you can get just a little bit better than the Autotunes. But the Autotunes will be more robust for all the different moves. I can't guarantee that I handcraft this move. If I make a different move, I'll get a similar, better result. The tuning algorithms tend to look at multiple facets and different move types. So you might be better off, if you're looking for robustness, just to stick with the Autotune. But if you have one specific move that your machine's making over and over and over, a little handcrafting by looking at all these different tools that I've shown you might be the best way to go. Just comparison chart here of those different techniques, and you can see no feed forward following 15.7 microns, and just that simple little hand calculation really drastically improves the overshoot by more than a factor of 2, and then auto tuning another factor of 2, and the handcrafting just slightly better. So let's talk a little bit about some nonlinearities. One that commonly is not thought about is the gain of the PWM amplifier. Typically, we just think of this as, current in times current out is just a linear scale factor. It's the gain of the amplifier. Or maybe at the most complicated, we think of it as, okay, there's some bandwidth to that system, so there's a roll-off, and it looks like a low-pass filter, and use that in our our modeling and in our mind when we do the tuning. However, if I would look at the loop gain of the system and measure that loop gain at high and low currents, and so here in the loop gain in the blue, I've measured the same system we've been working with that you saw in the videos. I've measured the loop gain with a current of 1 amp into the system on a 10 amp peak amplifier. And I have what would look like a normal loop gain to me. But then I rerun the loop gain with 0.1 amps and 0.01 amps, and I get the red curve that you see. And so there's a drastic difference in the gain of the amplifier, let's say from somewhere around 2 to 20 hertz. It's much lower when my current is very small. The PWM amplifier is not linear with respect to the current levels. And so what happens is when I do a point-to-point move, as I pull into the final position, let's say, that I'm trying to get to, the current output by the amplifier decreases because I just need less current to finish the move or move the mass. And so as that current decreases, the gain of my loop is actually decreasing. And so what happens is my settle time seems to just go on forever, when I wouldn't have expected it when I go back and look at, say, the blue loop transmission and go, I got lots of gain. Why am I taking so long to move in? Well, it's because at these low current levels, the gain of your amplifier, and this is a traditional PWM amplifier, and this is true of all PWM amplifiers to some degree, they have a gain loss at very low currents. So what can I do about that? Well, here's one thing you could do about it. You could measure the nominal current loop transmission and then get your standard gain set, and then do another measurement at very low currents and find a different gain set for the system, and then just use a little bit of gain scheduling to monitor the current level in the amplifier, and then when you get below some threshold, change the gain set of your system to help pull the system in more quickly. I wouldn't want to just do one loop transmission to make that decision. I'd run a family of curves like you see here on the right, and eventually you'll see some definitive kind of breaking point that says, okay, below this current, it would be a good idea to most likely increase the gains that I'm going to use and have that alternate gain set kick in when the current falls below there. A second area that we often run into is friction, and you can see that in the loop transmission here, that at the lower frequencies, below 10 hertz, I flatten out, and I don't really have that inertia line I would expect. This is an indication that I have some friction in the system. And so one thing that I can do to that to help my system is give up the phase. You can see that I have enough phase margin in the system that rather than raising the gain, what I'll do is give up phase so that I can get gain at the low frequency, and that will help me minimize my settle time. So if I look at a step move before and after giving up some phase, you can see that at the top, my settle time was 65 milliseconds, and on the bottom, I got it down to 27 milliseconds. So drastically decreased the time it took to get in position in this system. That's one way to help counteract the friction. Another is maybe to put a different structure in place. So here's a different control structure, and what it does is allow me to recover that inertia line in the system. As evidence, if you look at the green curve and the gain here, you can see that flatness, say around the 10 hertz area, and that is, again, evidence of the friction. And the blue line, when I put this new friction compensation in place, is matching the inertia line, as I would expect. And the result, if you look on the right side here, you can see a blue curve, which is with the friction compensation on, and the green curve without it on, and again, just drastically decreasing that settle time as you come in to the system. It doesn't just help with the settle time. On the top right, there's a contoured move. And the blue is the tracking error, and the green, blue is the tracking error with the friction compensation on, and the green without it. And again, you can just see a drastic increase in the ability to follow a contoured move. The last frequency response to discuss is the sensitivity response. This is the transfer function from the output error, the servo error of the system, to the input command, YD of S. And this is often helpful when trying to look at the stability of the system and look at instability points that might not be obvious in the standard loop transmission. So, for instance, here's a system, and if I focus on the left top chart, what you'll see is a frequency response that was run, a loop transmission, shown in the light blue color, and I have plenty of gain margin, so I just bump up the gain a little bit to get to the point where I have about 5 dB of gain margin. A little less than I would like. I usually like 6, but I'll leave it there. Still looks like the system should be quite stable. I enable the system, and I hear a little hum, and so I take and do a little snapshot of the system while it's sitting in place, and what I get is the chart on the top right. I see this 125 nanometer position error. It's what looks like a fairly higher frequency, and I'm like, well, why is that? Because, you know, my loop gain looks okay. Okay, so I'll do an FFT on this position error, which is shown on the bottom chart, and I see a spike at 200 hertz. So I go, okay, I'm oscillating at 200 hertz. Again, that doesn't make sense to me, because if I look at where the crossover is, where I'm looking at the gain margin, is 250 hertz. I wouldn't have expected it to be at 200 hertz. So what I'll do is then look at the sensitivity curve. And when I look at the sensitivity curve, I see just an obvious peak at 200 hertz. This is my problem. This is why I'm oscillating, right? So I can go back and to the loop transmission, I can lower the gain and make sure I have sufficient gain margin at that 200 hertz area, and that would resolve my problem. So the sensitivity response I find very useful at looking at robustness of the system. You'll see instabilities that look like peaks like this shown here much more easily in this response than you sometimes will in the standard loop transmission. So thanks very much for attending the webinar. I hope you found this information useful and you can apply this in your everyday life going forward. What we covered today was tuning the feed forwards, and we looked at 3 different techniques for doing that. We looked at 2 different nonlinearities in terms of amplifier gain at low currents and what friction looks like and how that affects the systems, and just 2 small things that we can do about that. I will do a 3rd seminar in January on sensor resolution and sample time. How do those affect the performance of the system? So hopefully you'll join us for those as well. And at this point, I'll turn it back over to Mark to conclude.
Well, thanks so much, Joseph. We do have time for some questions. The audience may type questions for the presenter in the Ask a Question box on the screen, and we'll get to as many questions as time allows. Questions that we do not get to will be posted online at www.controleng.com with the archived version of this webcast. Please remember to download a certificate of completion or a copy of the presentation by using the Event Resources tab on the left side of the screen. And now on to the questions. All of the examples shown in the continuous continuous domain or Laplace domain. What effect would a digital controller have on the results that you showed?
So thanks for that question. That's a good question. So the first thing is, often when we're sitting in front of the controller and using the tools that it has, the digital nature of the controller is hidden to us, and so we'll measure a response and we see the real response and change the gain, and so it at a basic level we don't really have to think about that very much. We can just change the gains and see the response of the system, and if it's good, it seems like it was a good choice, and if it gets worse, then go back to where you were. The one place that I did point out here in this webinar is when you're trying to insert the feed forward, that as a last polishing to try to get just a little bit better performance out of the system, paying attention to the fact that it's a digital controller and timing that feed forward correctly as an insertion into the current node will help.
Great, thank you. Next question. Let's see. You didn't mention what to do with the K sub V gain in the forward path. What's that for?
Right. So there are different ways to put the feed forward structure into the system. The most common is to use AFF and VFF, which are basically the inertia line, and feed that into the current node. But if you're using a multi-loop controller, you could also take and insert a feed forward velocity, say, into the velocity node, and that will also help with minimizing the overshoot of the system. It will also help with the disturbance rejection in the system, because when you would look at the sensitivity response, you'll see that will add a positive slope at low frequencies, and that positive slope is what will give us some disturbance rejection. Thank you.
Good, thanks. Another question. You showed tuning the feed forward for standard trapezoidal moves. How does that change for complex contoured motion?
Yeah, so the tuning for the feed forward, if you're just trying to tune for a specific move, the specific trapezoidal move, then you could use some of the techniques that I showed you, and particularly say maximizing the feed forward current to minimize the overshoot. If you're tuning for the contouring, I tend to like the method of matching the inertia line, matching the inverse feed forward with the plant, because I think that will give you a more robust solution for whatever contours are put in. Think of the contoured motion this way. It's an input of the command to the system, but I could break that command up into an FFT and give me a series of sinusoids or other types of moves, and they have some frequencies in them, right? So if I can match the inertia line best, then I'll cover more frequencies and not be tuning just for a specific type of move. So I tend to follow the frequency response method if I'm tuning for contours.
Great, thank you. If the audience would like to continue asking questions, we'll continue providing answers and, as long as we can, and get to the rest of the answers offline. Is it possible to cut? Oh, sure. Go ahead.
I'm sorry. I see a very interesting question here, so I'm going to jump in. So somebody asked, what's the difference between AFF and VFF, and where do I use those? I didn't really explain that too well as I was going along. So the AFF is really the acceleration feed forward. This is what you're compensating for the 1 over JS squared, okay? So if you looked at the current, the feed forward current, you would see this nice current that matches at the beginning and end of the move what the peak currents are as we accelerate. This is current during acceleration. The VFF, this you would minimize by looking at a constant velocity. So one way to do that is if you're doing, say, a standard trapezoidal move, just zoom in on the constant velocity part and look at the RMS current that is produced by the feed forward and the RMS current necessary to move the plant, and match those two up. And so change VFF so that those two currents are equal during the constant velocity move. And that's how you tune the VFF. And that doesn't necessarily always give you the best response during the acceleration. So the VFF may corrupt that a little bit. So there's a little bit of of handcrafting or craftsmanship here of picking the right balance between AFF and BFF, but that's the way to start picking it. So go ahead.
Great, thanks. Is it possible to customize the system for different loads?
Yeah, so there's two things you can do with that. If the load change is known, you could tune for each of the load changes, and then as the load is changed, put in a different gain set for that. If the load change is not drastic, then you could tune the system to be robust to just have one gain set that will handle the different loads as they change. If the load change is rather drastic and you really want to be optimal everywhere, there's not much choice other than to tune for those different load gains and measure something that knows when the load is changing and change those gains adaptively.
Good, thank you. Can you comment on how to best use the Autotune?
Yeah, so when you're using the Autotune, you want to make sure that you're stimulating the system at the right magnitude and with the right current. And so it's best to try a couple of different magnitudes and a couple of different currents. In the particular product I'm using, it will come back and give you a goodness of fit. And if your goodness of fit is, say, 70% or above, that's a decent fit, and I would accept those gains. And then I would run it a couple of times until my goodness of fit doesn't change. And once it stops changing, which is usually not more than 3 or 4 runs, then you probably have the best gain set that the Autotune is going to give you.
What signal are you using to excite the plant for your measurement?
So the signals is, there's a couple ways to do a runner frequency response. You can either do a sinusoidal sweep. You can insert white noise. There's another method called multi-sine, where you put in a sinusoid with an increasing frequency. The tool I was using has all 3 of those, and typically you'll see the signal inserted at the current of the power amplifier, and then measured at the input current command. But then it's just a bunch of arithmetic to get the different loop responses that I had shown here. There are other ways to do that. You can also insert the signal at the command part, in the position command, say, for instance. I like the power amplifier better because it gives you more control over the current, and I tend to get a much better signal to measure. So I get a much better signal to noise ratio when I'm measuring that way. And so that tends to be the way most controllers do it.
Great. Time for one more question. And as we answer that, please continue to submit additional questions because we'll get to those offline. Thank you. How many Bode plots should you be using to make assessments about the control loop? Depending on load location and offsets and so forth, you might have a variation in your Bode plot.
That's a hard question to give a particular number. How big is their system? What's the travel? How much does the load change? I would be probably look at what are your requirements of the system, right? So let's say you're trying to do a high performance system. The requirements are tight, and your load change is big. Then I probably would be doing quite a few Bode plots in different parts of the system. I usually like to run them at least twice in the same space, make sure I get about the same answer. I like to run different current levels. I like to also look at each of those different response types and make some assessment. But if I'm, let's say, tuning an XYZ system that's 500 millimeters of travel, I'm probably at least doing both ends of travel in the center for each axis at different current levels.
Well, thanks everyone for the great questions. We'll try to get to as many of the unanswered questions offline as we can. And thanks again to our presenter, Joseph Perfetta, for sharing his time and expertise with us. I'd like to extend special thanks to our sponsor, Aerotech, for sponsoring today's event. And now that we're just about done, we want to hear how we did. The exit survey will pop up on the screen when the webcast ends. Please take a moment to complete it because we use this information to improve our webcast. On behalf of Control Engineering and Aerotech, I'd like to thank you for attending. This concludes our webcast. Thank you and goodbye.